फाई हमारे 0 से लेकर
कैसे फाई तक है?
क्योंकि अगर हम एक बाल को अगर हाफ कर दे
so you have this hemisphere and you want to reach this point actually. So how you need to move? So you need to move, for example, first radially, okay, from origin outside, and then you have to move longitudinally, so that you can come right in front of the point, and then you need to move latitude. So मैं कह रहा हूँ कि when you are on sphere, no matter where you are, okay, you can reach to the every single point on the hemisphere by moving, in a longitude manner between 0 to pi by 2. Think about it. Pi क्यों नहीं? समझ आ रही है बात?
थीटा है सर, वो उस डिस्टेंस को
that theta can go all over actually.
वो उसको भी कवर कर लेगा.
So for example, if this point lies on the other side of the hemisphere,
stop there.
So you're gonna make all round along that point and then gonna come. The only glitch would be that how can I compute this volume actually? So this must be easy. If you want to compute the volume of V in rectangular coordinates, so it's going to be what? dx, dy and dz over this entire volume V, but you can turn it into this r square cos phi dr d theta and d phi, where r goes from 0 to a and phi goes from what? Phi goes from where to where? 0 to 2 pi, and theta goes from 0 to 2 pi and phi goes from 0 to pi by 2.
सर इसका वॉल्यूम तो हमें पता है ना सर, हेमिस्फीयर
वो कैसे आ रहा है? So how do you know that its volume is? So you say that 4/3 pi a cube actually, or 2 over pi a cube actually. But question is, how do you know this formula? So if you really are computing it, think about it. So it's going to compute it, it turns out to be that formula.
Sir, I am in trouble, sir. If we will take whole sphere, then what will be the limits for phi? Because if we are using this intuition in that case, so then
वहाँ पर भी तो minus pi by 2 से pi by 2 तभी ले रहे हैं ना. Think about it. So you want to reach point. So if you have a spherical thing, okay, you want to reach some point here actually. So you need to pull out, make an all angle somewhere, and then go down actually. Okay, so you need to take the negative latitude.
So इसमें minus pi by 2 से pi by 2 होगा.
क्यों minus pi by 2 से pi by 2? ये hemisphere है बेटा पहले.
सर टोटल वॉल्यूम जो कंप्यूट कर रहे हैं
तो हम इस hemisphere का वॉल्यूम कंप्यूट कर रहे हैं. So this V doesn't mean the volume of entire sphere. So this entire problem is about the hemisphere actually. So
ये पोर्शन उसका वॉल्यूम अलग से कंप्यूट कर रहे हैं और हेमिस्फीयर का अलग से.
किसका वॉल्यूम? अगर for example if you want to compare the volume of sphere, then you just need to change this to minus pi by 2 to pi by 2. That's it. That's the only change that you need to make in this integral and nothing else actually. Everything would be same. It turns out to be this 4/3 pi a cube actually.
So मैं ये कह रहा हूँ कि मतलब हमें given हेमिस्फीयर है उसमें से भी एक छोटा सा पोर्शन ले रहे हैं.
उसमें से पोर्शन नहीं ले रहे हैं, हम तो entire hemisphere दे रहे हैं. So on a hemisphere, give me a point where I can't reach by choosing the r between 0 to a and theta between 0 to 2 pi and phi between 0 to pi by 2. So give me any point actually that you have in your head. Okay.
सर फिर इस टोटल वॉल्यूम और उस वॉल्यूम में डिफरेंस क्या होगा?
बेटा डिफरेंस ये होगा कि this would be the half of the sphere volume actually. So this is going to be 2 over pi 3 pi a cube, not 4 over pi a cube actually. That will be the central difference actually. ठीक है, so it's going to be 2 over pi a cube, not 4 over pi a cube, because this is not easy there. ठीक है?
Yes.
Good. So this intuition we need to develop. Think for yourself in the head. You take this sphere, take something spherical. I should have taken something spherical with you so that I can really show that, okay, where you want to reach on this sphere or hemisphere actually. You only need 3 quantities. And if you are on hemisphere, you can reach to any point by traveling, say, for example, from origin along radially, and then theta could be any point between 0 to 2 pi. In other words, you can go all around the sphere actually, and for phi I don't need to minus pi by 2 to pi by 2 in case of the hemisphere, because I just need 0 to pi by 2 in the hemisphere actually. Yes, if I'll take this as a hemisphere here actually, it's just like you can see that the really you turn this upside down. Okay? तो फिर क्या होगा? फिर then your limits would not be 0 to pi by 2, then it would be from minus pi by 2 to 0 actually.
Yes.
Minus pi by 2 to 0.
और सर उसकी थीटा की सेम रहेगी फिर?
वो थीटा और वो सेम रहता है।
और वो भी माइनस ए से 0 होगी फिर?
नहीं वो a से 0 होगी, रेडियस का भी नेगेटिव।
अच्छा सही।
It's going to be always ठीक है, it's a little bit okay. What is the next thing? The next thing. There are some examples similarly in the exercise sheet as well. They're not loaded. Think about now. Cost averages too. Last time someone asked me a question, I remember. So we made a triangular region. So we said I have this xy axis. We have this triangular region actually. And then we said that this is a curve. And then we said that our curve should be smooth actually. And someone raised the point, the curve has the coordinates. Okay? The curve has the coordinates. The curve has the coordinates actually. Okay, so how can it be smooth? That's a valid point. Because we don't want smoothness but piecewise smoothness.
Yes.
Okay? So we don't want to treat this as entirely a smooth curve, but it's piecewise smooth curve actually. Okay? And similarly, now I would like to define what do you call piecewise surfaces. So in other words, you have a surface. Okay, so you have a surface. But that surface is not really a one single piece. It's a combination of different surfaces. For example, think about this surface actually. The boundary of this surface. You can't say that this is just one single piece actually. Okay? So this surface, this white part is different from this big bottom part actually. This is a different surface. And this cap is a different kind of surface actually. And the top is a different kind of surface. So in other words, there are, really 4 or 5 surfaces put together is creating really this, what do you call this surface. So what surface should we call it? Okay. So it's kind of a piecewise surface where you have different surfaces and you are putting them together to consider it. And now I would like to, talk about the Gauss theorem. And I need to define a similar kind of surfaces which are piecewise smooth. Parametric piecewise surface. So here's the definition. So we're going to say that I have a subset S of R3 and it's piecewise parametric surface. Piecewise parametric surface. surface. Okay. If there exists one subset or maybe more than one subset of S such that E is union of finitely many points. Okay. And our curve segments could be R. Curve segments. And the second part is that if you throw away this S from E, okay, then what? S is a parametric surface. The S minus E is a parametric surface. What do you mean by parametric piecewise surface? So imagine you have this cylinder. Let's take a cylinder. And let's take a plane over it. Let's put a plane over it. So this is a cylinder that fits on last time. Is this a piecewise parametric surface? I'm going to say yes and no. Why?
Plane
Where they are different, think about it. The real trouble-making points are these points where they are being attached with each other actually. That's what makes them different. Okay? Think about it. I think, so if a welder is doing the welding, he's going to take this boundary of the cylinder is going to attach it with this lid actually. I say. So in this, so if you compare with this definition, so that's a parametric piecewise surface, so piecewise parametric surface. So what should be the analog of E? So the analog of E is going to be these points actually. Are you getting the point? Yes. The analog of E is going to be these points. So these collection of the points where this lid or this plane and this, what do you call, cylinder are meeting with each other, the sheet and cylinder are meeting with each other, are the points E actually. So this is what its union of, could be some finite point or it could be a curve actually. Think about it. Okay. And if you remove, and I'm treating the union of both of these, so the combination of both of these as the, what do you call it, surfaces. Then if you take this S and remove this boundary out of, what do you call this surface, then this is a single piece actually.
Yes.
So how you can turn these two pieces into a single piece? You need to really join the boundaries of it actually. So welder ko weld karna padega to kya karega? Think about it. So he has to weld these boundaries and put them together. And now you can treat that as a single piece actually.
And we will subtract this surface area because it is
subtract you need to I mean, except at all these points you can treat this as a single piece actually. So this is really the controversial point actually. Okay. So instead of, for example, you're taking a cylinder, you take a sphere and put it on the top of it. Okay. That's the same case. So you have two surfaces with the parameterization where they are meeting at some local finite curve actually. Okay? So it's one curve. So if you ignore this curve, you can treat them as a single piece. Or if you join them through this curve, then these two are really the single piece actually. Think about it.